Something was terribly wrong, and it felt like the entire world had gone mad. The year was 536 CE, and several months ago a high black fog rolled over the European continent and has remained ever since. Immediately thereafter, the sun seemingly dimmed, and it was so dark that it looked like twilight at noon. Crops started to fail, and despite it being summer, it was cold, too cold, unseasonably cold. Even the wealthy were starving, and everyone in their weakened state suddenly started becoming frequently sick. Even the ability to see one's shadow seemingly vanished, and what glimpse you could get of the sun made it appear a slightly tinted blue color. This was the worst year to be alive in recent human history, and it was about to get so much worse only 4 years later. What I just described are all symptoms of a deadly volcanic winter, the destructiveness among societies of which has not been surpassed in the modern period, not even in 1815 to 1816 from Mount Tambora, which caused the year without a summer. And yet, scarily enough, we have no truly conclusive evidence, meaning we don't know which volcano produced such a major eruption. Yet, due to new research combined with my knowledge of world volcanoes, we may have found several good candidates for this mystery eruption. What you are looking at is one of those volcanoes so remote and isolated that this footage might be the only video of this vast volcanic crater in existence. Located in incredibly remote western British Columbia, this sizable crater, which you can get an idea of how large it is via the many trees noted here, is seemingly the youngest vent of a little-known active Canadian volcano, the Spectrum Range. So, how did such a remote volcano seemingly contribute to the beginning of one of the worst periods to be alive of the Common Era? The answer involves large amounts of sulfur dioxide ejected into the stratosphere. When tall eruption plumes from large explosive volcanic eruptions reach the stratosphere, it reacts with water and oxygen in that layer of the atmosphere to form sulfuric acid. Sulfuric acid has the ability to block substantial amounts of sunlight, sometimes even in the double-digit percentage range, and can remain in the atmosphere for around 3 full years. For proof of this concept, here is a chart from the Mauna Loa Observatory which measures during a clear sky day the percentage of sunlight that hits the ground. While normally this figure would hover around the 92 to 93% range, there are multiple instances since 1958 when a large volcanic eruption caused this figure to rapidly drop. The most severe of these was in association with the 1982 eruption of Mexico's El Chichon volcano, as its rising magma interacted with a thick layer of anhydrite, leading to unusually large sulfur dioxide emissions for an eruption of its size. As a result, 7.5 million metric tons of sulfur dioxide were ejected into the stratosphere, leading to a 13.43% reduction in the amount of sunlight hitting the ground at its peak. And it would take 3 full years for this reduction to return to pre-eruption levels. Yet, eruptions up to nearly 2 orders of magnitude larger have occurred in historic times, leading to temporary reductions in the amount of sunlight hitting the ground by as much as 67%. For reference, such a severe worst-case scenario impact is equivalent to it never getting any brighter on April 26 in Phoenix, Arizona than it would normally be a mere 85 minutes after sunrise. This caused crops to fail, or if they do not fail, to be heavily stunted, and with suddenly too little food and too many mouths, people starve. Angry at their situation, wars, insurrections, and rebellions are more likely to start, regardless of the governmental structure in place. And to top this all off, diseases start spreading at an increased rate. This is exactly what happened when 4 years after 536 and 540 CE, another massive mystery volcanic eruption occurred, compounding the already present volcanic winter. Normally, sunlight, specifically ultraviolet radiation, would kill deadly bacteria such as Yersinia pestis, the culprit behind the plague or Black Death, to die after around 30 minutes exposure. However, with reduced sunlight and ultraviolet radiation, this would allow bacteria to survive for far longer, causing the R0 of a disease to increase, resulting in an exponential increase in cases than there otherwise would have been. And this is exactly what happened when, in 541 CE, the first plague pandemic known as the Plague of Justinian began, leading to the eventual deaths of 50 million people. The length of the worst phase of this pandemic was further lengthened when in 547 CE, a third mystery eruption occurred, once again lengthening the Volcanic Winter and its effects. So, how severe exactly were these three volcanic winters, taken in isolation if we ignore their overlapping effects? Thanks to a scientific paper published by E. Jungklaus and others, we actually know. The January or March 536 mystery eruption blocked up to 55% of sunlight from reaching the ground for a time. The January 540 mystery eruption blocked up to 61% of sunlight, and the 547 eruption blocked up to 5% of sunlight. These eruptions all seemingly occurred in the northern hemisphere at around 42 degrees north latitude, 15 degrees north latitude, and 42 degrees north latitude respectively. Adding to this, they seemingly involved around 18.8 million, 31.8 million, and 1.1 million metric tons of sulfur dioxide entering the stratosphere respectively. I want to note that a number of factors can cause a volcanic eruption to produce an undersized, average, or oversized volume of sulfur dioxide emissions for what is expected of its size. One of these factors is silica content, which is generally inversely proportional to the amount of released sulfur dioxide. In other words, when regarding a large low silica basaltic eruption, which is the same size as a large high silica rhyolitic eruption, the former will almost always eject a larger amount of sulfur dioxide gas into the atmosphere. Using this, I have made a chart which attempts to estimate around what size our three mystery eruptions would be about depending on their erupted lava's silica content. With that in mind, I will briefly go over large eruption candidates which for one reason or another turned out to not be our mystery eruption culprits. Iopingo's caldera-forming eruption in El Salvador was dated to 535/536 CE in one paper, but later more accurate dating shows it erupted within 2 years of 431. While Krakatoa did have a caldera-forming eruption larger than its 1883 eruption, despite what one historical source claims, there is no evidence it produced such a massive eruption in the 5th or 6th centuries. One of Sudak's caldera-forming eruptions is too old, while these other 5 large eruptions occurred too recently. However, when scientists looked at ice cores from the period of 536, they found not 1 but 3 sources of tephra for that year. It was not one massive eruption that caused the year of hell, but 3 closely spaced but still large smaller eruptions. While it was difficult to pin down any distinct volcanoes from the limited data, there was a good match for 3 regions, all of which were in North America. First, the Mono Inyo volcanic chain in California. Second, a volcano within Canada, which was part of the Northern Cordilleran Volcanic Province. Third, some volcano in the Aleutian island chain. Looking at California's Mono Inyo chain, we have a perfect fit. This complex is rhyolitic, produces massive rhyolite lava domes, has produced multiple Holocene Plinian eruptions, and clearly did erupt in 535 or 536. However, there are 3 clusters of vents whose margins of error in terms of calibrated age dating overlap with the aforementioned date, and we are unsure which of these 3 represents the eruption we are looking for. They are Wilson Butte for Cluster 1, the Amphitheater Crater, Orchestra Pit, and Rocket Thruster's Mare explosion craters along with the South Coulee lava flow for Cluster 2, and the Pumice Pit Dome, its possibly associated Mare explosion crater, and the Northwest Coulee lava flow for Cluster 3. Let's for now assume that Cluster 3 is the best fit. That eruption likely emplaced the voluminous northwest Colli lava flow that measures 1.3 miles wide, which I estimate has a volume of 0.35 cubic kilometers, implying the source eruption involved an unusually large batch of magma. This eruption also emplaced the much smaller 1,800-foot wide pumice pit dome. However, surrounding this rhyolite dome is what appears to be a raised rim that is 4,700 feet wide, possibly representing a massive Mar explosion crater. If this Mar did indeed exist, it was likely almost completely infilled by tephra from the subsequent Plinian eruption of Panem crater in 1340 CE. Heading to the north, we have a potential eruption from Mount Ziza or the Spectrum Range volcano, as these are the only two regional Canadian volcanoes with an apparent potential to produce VEI4 or larger explosive eruptions. While there is a large margin of error on the age of the Sheep Track pumice eruption from Mount Ziza, it appears to have originated from a trachyte crater recently uncovered by glacial retreat. Yet, by all estimates, while large, this eruption was only a high-end VEI3, too small to contribute to a volcanic winter. However, to the south, there is a large area on the little-known and little-explored Spectrum Range volcano covered by thick black ash deposits, where a more than 12 square kilometer region is buried by around 10 meters thick of ash. This ash seemingly originated from a single eruption that formed the ash pit, which created a 100-meter deep and 750-meter wide explosion crater termed a Mar in the ground, and what you are looking at may be the only photographs and video footage of this absurdly remote feature. We currently have absolutely no clue when this feature formed, but an age within the last 2,000 years is seemingly supported by visual evidence. This eruption was presumably of a basaltic andesite or tephritic composition, and subplinian or plinian, therefore a fantastic candidate for a large input of sulfur dioxide during 536. As for our Aleutian Mystery Volcano, we come to our weakest link of the three. Currently, we only know that three volcanoes had the potential to produce large eruptions and had at least one dated eruption whose margins of error give it the potential to have erupted in 536. These are Redoubt, Acotan, and Seguam. The first two I can immediately exclude, while for Seguam it contains the large 400 million cubic meter viscous lava flow that may have formed within its youngest caldera. Yet, at most, I could only see an eruption which produced such a feature as ejecting around 0.4 cubic kilometers of tephra. For the current evidence to work, the Alaskan eruption must have been at least 5 times larger than either of the other two eruptions in 536, with this not seemingly being supported by a possible Seguam eruption. However, somewhat close by there are two large undated calderas which are just the right size to fit the sulfur dioxide production profile from a Plinian basaltic andesite or andesitic eruption. They are the youngest caldera of the Yonaska volcano and the caldera of the Herbert volcano. Either one of these, while unproven, could be our third mystery eruption source. And by combining these three candidates, my likely overestimates of each eruption size when added together potentially work. What about the 540 CE mystery eruption? We are pretty sure per current sources that it occurred between the equator and 15 degrees north latitude, while many sources have correctly noted that Mexico's El Chichon volcano erupted in 540, and that the local Maya were severely affected. There is one crucial problem. Current evidence places that eruption as far too small to be our culprit, only registering in on the volcanic explosivity index as a 3. We would to somehow be underestimating that eruption's size by a factor of 50 to 100 for it to be our 540 CE mystery eruption culprit, a possibility which is not supported by current field evidence. However, outside of North America, I have one potential candidate to note, although I want to add that the 540 CE eruption could have also occurred at some unknown undated caldera. We know for a fact that a major VEI-6 explosive eruption occurred from the Sigl volcano at 14 degrees north latitude, by the way, sometime between 3000 BCE and 1000 CE. This unit is estimated to have a volume of 46 cubic kilometers of tephra, a perfect match for our expected size of our mystery eruption. As for the much smaller 547 CE mystery eruption, I analyzed and made a list of all 20 volcanic eruptions in the expected VEI 4 to 5 range whose dated margins of error mean it could have erupted in 547. Yet, since we are pretty sure it occurred in the northern hemisphere at around 42 degrees north latitude, we can narrow down this list to 4 volcanoes. 2 excellent potential matches appear to be the Rasudake and Haruno-san volcanoes in Japan. And those are the volcanoes whose eruptions may have caused a period during the early Dark Ages to actually become somewhat dark. Of course, much of what I just proposed is untested, and I did a lot of speculation. I encourage fellow geologists to analyze the volcanoes I highlighted to see if there is any plausibility or lack thereof to support them as mystery eruption candidates. A special thanks to everyone who has supported this channel through my many patrons on Patreon and channel members on YouTube. I would not be able to make long-form content like this without your support. Be sure to share this video around if you want me to publish more long-form content, as it takes me a lot longer to make videos of this length.